Welcome everyone to this lecture. My name is Mikael Ingemyr. I am Secretary General at the Swedish Astronomical Youth Association. Astronomisk ungdom in Swedish. We in the Swedish Astronomical Youth Association, we work to promote interest in astronomy and space science among kids and adolescents in Sweden. And one of the things we do is talks, space camps for kids, and Swedish summer science schools. And now, this evening, together with Astronomiska föreningen, our local organization here in Uppsala, and Vasco and Uppsala University, we're happy to host this very special talk this evening. And with us, from the Department of Physics and Astronomy, to introduce tonight's speaker, we have Professor Ulf Danielsson. Welcome.
Thank you. Thank you very much. I'm a cosmologist, theoretical physicist. I do string theory and things like that. But as an aside, I'm really interested in the kind of stuff that we will be hearing about tonight. I'm really looking forward to it. And I'm really truly honored to be able to introduce to you Professor Pete Worden. His list of merits is very long. He got his PhD in astronomy from Arizona University. He served for decades in the US Air Force. He's been a professor of astronomy at Arizona University, and for more than a decade, the director of the NASA Ames Research Center. All of this reflecting a lifelong engagement in space exploration. He's also rather famous for criticizing NASA quite harshly, actually. And after he got his position as a director at NASA, he's famously quoted as saying, "I learned you have to be careful what you say about an organization because you could end up working for them." Keep that in mind. Okay, currently he's chairing the Breakthrough initiatives, channeling a massive effort to reach out beyond the Earth. These include breakthrough listening, searching for alien communications, using radio and optical telescopes, and perhaps even more breathtaking in a way, the Breakthrough Starshot, developing a fleet of light sails that could reach Alpha Centauri in 20 years. Today, he's going to tell us about an exciting future. Please.
I did want to talk a little bit about the Breakthrough Prize. As I mentioned, Yuri Milner felt that it was important to encourage the next generations of scientists that will produce the discoveries that a century from now will produce new wealth. So he established the Breakthrough Prize in Fundamental Physics. His idea was to make it the biggest prize in science. I guess I'm a little embarrassed to say that the next biggest prize is here in Sweden, but it's $3 million US. Since then, he's had other high net worth people, including Mark Zuckerberg from Facebook, Sergey Brin from Google, Andrew Wisky from 23andMe, and now Pony Ma from Tencent, and for a while Jack Ma from Alibaba, that have sponsored these awards. Well, the way I got involved with this was that about 6 years ago, as the director of NASA's Ames Research Center, my chief of staff came in and said, the Vanity Fair people are here to see you. I said, Vanity Fair? I said, was it my nice clothes they were interested in, or the good scientific, kind of, they want to do a fashion show for scientists? And I said, no. That apparently Yuri had asked them to help organize a ceremony. In addition to giving the prize, decided to have a really cool ceremony, and they wanted to hold it in Silicon Valley, and on the campus of NASA Ames. We had these really neat old airship hangars, and so we held them there. And since I was the landlord, I got invited. And so that's been going on here about 6 years. It's a very neat ceremony, and I have to say, although it's probably quite an honor to get the Nobel Prize from the King, that we decided to have God give our prizes. So for the last 2 years, we've had Morgan Freeman give the prizes. It's a pretty cool ceremony. The prizes are presented. This is Helen Hobbs, who discovered a heart disease genetic inhibitor. We have 5 prizes in life sciences. It's presented by a high net worth person. You probably recognize the kid on the right there. The one on the left is an actress, Hilary Swank, and I can never remember her name, but I knew her that she played in Buffy the Vampire Slayer, so kind of cool stuff. One of the neat things we did, just as about 3 years ago, we decided to in addition to our main prizes and our early career prizes, which are $600,000 prize for early career researchers, we also decided to do a junior challenge. And we asked young people to make a few-minute video on some science principle. The winner gets a $250,000 US scholarship. The school gets a $150,000 laboratory, and the teacher gets a $50,000 check that the student says inspired them. Incidentally, the first year that we had it, the young man didn't tell his teacher that he'd been nominated. And so we called up the teacher and said, "Where do we send your check?" He wanted to know if this was a call from Nigeria. But in 2016, we actually had 2 prizes. These were both young ladies, which was kind of neat. One was Deanna C. from Singapore. The other was Antonina Massini from Peru. And this last year, this young lady, Hilary Andales from the Philippines won. So it's really been kind of neat. I chair the selection committee, so it's a pretty cool activity. But one of the other reasons I'm here is today, I think we released the 2019 prize procedures, and we'd like to see nominations from a place that's won a lot of Nobel Prizes. So it's an open nomination process. It's an online process. I think it closes the end of May. The procedures are online, given here. It is a pretty neat prize. It's a pretty open selection process. After the nominations, our selection committee are the previous winners. So I would urge you, if you have a colleague, you can't nominate yourself, to get somebody to nominate. But I'd like to spend most of my time talking about the question of life in the universe and the breakthrough initiatives. And by way of background, sort of one of the rationales behind this is sort of an existential one. There's a lot of bad things that can happen to our society. One of those is, of course, something could hit the Earth. Of course, the ultimate one, which is maybe pretty much of an argument, but I will say that since you're a string theorist, and Yuri Milner started out in string theory, that there's this idea that the universe is some sort of nth dimensional quantum state, and the question is, it's stable or unstable or metastable, and if it's anything other than fully stable, there's the idea that the universe may shift states at some point, which creates what I think it's called a death bubble, which is kind of a cool thing. So this may have happened somewhere in the universe already, although it sort of raises, there's not much we can do about it. Actually, there is, but it raises really 3 fundamental questions, which I think Yuri and a lot of other people are very interested in sort of looking at. The first one is there any other life in the universe? And one of the questions is sort of realizing that we may be kind of temporary, is to really ask that question: are we really alone? And if we're not alone, is there intelligent life elsewhere? And maybe the ultimate one is, can we travel between the stars? By the way, I guess if you get close enough to the speed of light, maybe you can outrun the death bubble as the accelerating expansion of the universe takes you away from where it is. That's, again, a good argument over many drinks. But let me talk a little bit about life. And I'm not a biologist, I'm an astronomer by background, so I'll probably get this goofed up. But life on Earth probably arose 3.5, maybe 4 billion years ago, very early on in the Earth's life. That life and throughout most of the history of the Earth was a very simple form of life, what are called prokaryotes. Fairly simple genome with maybe a few million DNA base pairs. Simple coding, which at least we kind of think we can understand. But the interesting thing is somewhere around 1 billion years ago, give or take a few 100 million years, a second form of life emerged, which are called eukaryotes, which have a far more sophisticated, maybe not sophisticated is the right word, complex existence. The nucleus has got a lot more genetic material. It's encased in a membrane, and it actually has access to about 1,000 times more energy than a prokaryote. And this is what gave rise to all sort of complex forms of life on Earth, including us. Now, everything seems to have originated from a kind of one simple source. In fact, about 25 years ago, we discovered there's two kinds of prokaryotes. The second one, called archaea, we didn't even know existed for a long time, but you know, a good bit of the biomass on Earth is archaea and not bacteria. But what might have happened, or appears to have happened, was about 1 billion years ago or so, as I noted, that a archaea cell engulfed bacteria, and rather than digesting it, it formed a symbiosis. And where the bacteria continued to exist inside the archaea and ultimately produces the cell's energy. This, as I noted, increased the amount of energy the cell could make use of, which allowed a much more complex genome and potentially much larger cellular organisms. The energy-producing organelles, they're called, in the case of animals, are mitochondria. In the case of photofluorescent or photosynthetic plants, they're chloroplast. So this kind of raises the question, is this a standard process? That maybe we'll find that there's life everywhere, but it's all simple, that this sort of was a unique, singular event where you had this sort of symbiosis. So this sort of raises three alternatives as we look for life. The first one is that life itself is very rare and maybe even singular. We may be very much alone. The second alternative is life is very common, but this symbiosis and the complex life forms that could give rise to what we call intelligence is rare or even singular. We may be the only intelligent species in the galaxy or even the universe. So we're still alone. The third one is that life may be very common, and so too is intelligence. So our primary objective is really to begin understanding these questions. Not to say that this hasn't been looked at for a long time, but we think technology and resources are now available to really do a much more sophisticated job. So on July 20th, the anniversary of the Apollo launch, or Apollo landing, the Yuri Milner, along with Stephen Hawking, who's our senior science advisor, announced in London the Breakthrough initiatives. And I'm going to tell you about these initiatives. We've added several since then. But the first initiative was Breakthrough Listen. This was a primary question to really revitalize our effort to look for signals. In the late 50s and early 60s, the first real scientific efforts to look for signals began with the observational one was Frank Drake and Carl Sagan, who was a student working with him. I'd always thought as an astronomer, well, we'd looked, we didn't see anything. But in fact, we hadn't looked very hard. That's one of the first things that we discovered. Now, I do want to make clear that this is not about looking for alien visitations. And I think this has been one of the challenges in scientific work on SETI, is that very soon somebody asks you if you've had a ride in a spaceship. I served for 29 years in the U.S. Air Force, and no, I wasn't aware of any classified effort. Although I think there was one that was based on trying to, pay off some senator that had some people that wanted that. We can talk about that over a beer too. But what we're really about is looking for signals. And the first thing that we recognized is that in the past, access to data, both radio and then later optical data, was hard. So one of the things we could do is, since Mr. Milner committed $100 million US for the next 10 years, is actually buy time. So we bought 20% of the time on this. This is the U.S. Green Bank 100-meter telescope in West Virginia. It's the world's largest steered radio telescope, 100 meters in diameter. We also acquired 25% of the time on this telescope to look at the southern sky. This is the Parkes 64-meter telescope in New South Wales in Australia. This is kind of an interesting telescope. It actually was the one that received the Apollo 11 moonwalk data. There's a really cute Australian movie called The Dish about it. It's actually one you can show your family. There's no naughty words or anything, and it's pretty cool. They play cricket starting in The Dish. Noting again that there's potential optical signals, and increasingly we're using optical communications. Using a telescope on the Lick Observatory called the Automated Planet Finder, which is a 2.4-meter telescope. By the way, it isn't where the laser beam is coming from. That's the 120-inch at Lick. There's a small white dome that's kind of in the center of the image. We have been working with the Chinese. Signed an agreement about a year ago to use what's now the world's largest radio telescope. This is not a steered antenna, but a fixed dish. It's 500 meters in diameter. Pretty cool. We'll be having a conference with the Chinese here in a few months to begin those observations. We also have got other agreements. We signed an agreement with the Jodrell Bank in the UK, which is a 75-meter radio telescope. It was the first really big radio telescope, modern radio telescope, built in the early 50s. And we're just now completing an agreement with what will eventually be the world's largest radio telescope, the Square Kilometre Array in South Africa. The first 64 dishes, called Meerkat, are finished, and we'll be using this in what's called a commensal mode, where we can use the auxiliary beams of it to look at the million nearest stars. So that should give us a thorough search out to about 1,000 light years of anybody that might be trying to signal us. Now, we also announced something we call Breakthrough Message. And this is a kind of a controversial area. Should we be trying to message anybody? We early on said, well, if we did anything on this, we wouldn't actually try to send messages, but we'd think about it. And so we eventually had planned some contest globally to both think about technical ways you would do communication and encode things, as well as what you would put in it, pictures. However, among other people, Professor Hawking thinks it's a bad idea, so we put that on hold. Although I will say that there's been some things done on this, and it's become quite controversial. This is the famous Arecibo message in 1974 that Frank Drake and Carl Sagan sent. This coded messages to a star cluster 25,000 light years away, so we have a bit of time before we get an answer. I'm not sure I would figure out much from it. I guess it's supposed to be DNA. I think that's supposed to be humans on the bottom. So if we sent a message like this, I'm not sure this would communicate very much. But at any rate, this is an idea that's still open. But I want to emphasize that the breakthrough initiatives are putting this in abeyance to avoid getting into too many arguments. Now, as mentioned, of course, probably to me, the most exciting thing, because I always wanted to do this since I was a teenager and read science fiction, can we travel between the stars? And this is quite frankly why Yuri Milner persuaded me to leave NASA, plus the fact the administrator didn't like me, because I made statements like that NASA stood for never a straight answer. Still true, probably. Although they did interview me a few months ago to see if I wanted to be the administrator. No. Yeah, that's too much trouble. But at any rate, the question of going between stars, I think, is a big one. So on April 12th, 2016, which was the 55th anniversary since Yuri Gagarin's historic flight into space, and I might add that Yuri Milner was named after Yuri Gagarin. He was born a few months later. So he had an incentive, I think, to do something on this. But we made this announcement, as I said, on April 12th, 2016, in the New World Trade Center in New York City, with Professor Hawking. Also, Freeman Dyson, who's talked about interstellar stuff for decades, Ann Druyan, who was the creator of the Cosmos series, and Carl Sagan's widow. Professor Avi Loeb, who's the chairman of the astronomy department at Harvard, chairs our oversight committee. Mae Jemison, a former astronaut who has done a lot of work on interstellar efforts, and then there's that other guy, the bureaucrat. But of course, the question is there any place to go? Which is kind of a big question. I would have said when I was a graduate student, we thought maybe 1 in 10,000 stars had a solar system, and maybe 1 in a million had a planet like the Earth. We're discovering that there's a lot more solar systems out there. This was a mission that I'm very proud of. It was led by NASA Ames and formulated at NASA Ames, one of NASA's 10 centers, the one I ran. I think, to my mind, this may be the coolest mission ever. Of course, you always think that your mission is. In this case, it's true. But it looked at about 100,000 stars like the sun, and every half hour, in some cases more frequently, just measured the brightness of that star. And we were looking for a shadow event where if the orientation of a planetary orbit was correct, and a planet traveled in front of the star, you'd see a small dip in the starlight. Now, a planet the size of the Earth doesn't produce much of a dip. It's about 30 parts per million. But been spectacularly successful. There have been thousands of planets discovered, and dozens that seem to be the size of the Earth, and many in what's called the habitable zone. Since then, there's been a lot more work. I'm really intrigued by TRAPPIST-1, which used other systems to do a similar thing, look for the shadows. But TRAPPIST-1 is some 30, 40 light years away. It's a red dwarf star. It's much smaller than the sun, but it's like 70 or 80% of the stars in the galaxy. And TRAPPIST-1 has 7 planets that are more or less the size of the Earth. 2 or 3 of them are in the so-called habitable zone, where liquid water could exist on the surface. So the question is, could we go to these places? Well, the fastest and furthest thing we've sent are the Voyager probes. They're about 120 to 130 times further away from the sun than the Earth is. But the nearest star is 300,000 times further away. So at the speed these things are going, we would get there in about 60 or 70,000 years. Unlikely to even have visionary billionaires fund those efforts. And we've decided our targets should be the nearest star system, the Alpha Centauri system. It's 4.3 light years away, and I'll talk more about that in a second. But we set an objective and said, can we send a spacecraft to this star? Maybe some other ones that are within a few parsecs or maybe 10 light years or so from the Earth. Can we return scientifically useful data that could begin to answer questions about life there? And can we launch something within about 30 years for a reasonable cost and get there in about 20 years? So it means we had to go 20% the speed of light. Well, going 20% the speed of light is about 1,000 times faster than we can go today. Is this something we can think about doing? Now, in the middle of the 20th century, we did increase the speed a factor of 1,000. It was kind of a logarithmic, log linear plot. But since the space age began, we haven't really done much. So one of our big questions is, can we get back on this sort of exponential increase? We established an advisory group, several of whom actually won this cool Swedish prize. Some of them won our Breakthrough Prize. And we put together a study team. And as I said, Professor Loeb from Harvard chaired that. They considered all sorts of approaches, and most of which are silly, but we looked at them anyhow. Looking at standard and exotic propulsion. This is the only equation I'm going to put up, but it is a significant one. It's a rocket equation. Maybe just to mention that one of the key things is it's a dimensionless parameter called the specific impulse. You can kind of think about how many kilograms of thrust do you get for so many kilograms of fuel. A typical rocket today, a chemical rocket, this number is somewhere between 300 and 400. If you look at this equation and say, I'd really like to go 20% the speed of light with some reasonable mass, you can calculate that if you had a fuel that had, rather than a few hundred specific impulse, had a few million, that would do it. So that's called the magic million. This has been looked at, and it's hard. As I said, you could use chemical fuel, but you can calculate from this equation the amount of mass that you need in fuel is about the mass of the galaxy. So we're probably not going to do that currently. You can potentially use nuclear energy. There have been fission and fusion rockets proposed. We looked very seriously at these, but the problem is it's like fusion anything that, fusion energy, when I went to school, was called the energy source of the future, and somebody said it always has been and always will be the energy source of the future. So the thing I was initially very excited about was antimatter. Everybody that watches Star Trek knows they use antimatter, which, by the way, if you have a matter-antimatter reaction, it gives you a specific impulse of close to 10 million, so easy. The trouble is producing antimatter. You can produce it in a particle accelerator at about maybe 10 to the 13th, 10 to the 14th particles per year. There's a little issue of storing it because it does detonate when it meets normal matter. But we would need something like 10 to the 28th particles, so that's probably also in the future. Although I will say there is a group, this is a group of young people that have been funded with a startup called Positron Dynamics. They're developing, anti-electrons, positrons, and using those to induce fusion. They are doing experiments, and it's very interesting. I put this paper up largely because it's probably rubbish, but it's the most cited paper in the Journal of Propulsion and Power, and it was written by a NASA guy. It was actually a good friend of mine, and he's a physicist, but he, this is sort of like free propulsion. He put a bunch of microwaves in a cavity and bounced them around and got a net thrust. It's most likely a poorly done experiment, but I was talking to the Chinese about a year ago, and the deputy head of the Chinese Space Agency asked me what I thought of it, and I said, well, I think it's rubbish. And he said, well, I do too. He said, but our physicist also thought it was stupid, but we tried it on the space station, other space station, and it worked. So we'll just leave that there for the moment. If they do make it work, then we're going to drop everything we're doing and go to this. However, we decided to go back to something we know works, and this is sailing, where the energy source is either gotten from the environment or kept behind. This is an idea that is a lot of, been thought about for a long time. Actually, Kepler wrote a letter to Galileo, which roughly translated, says that, if you build a sailboat for heavenly winds, you could venture into the great vastness. Now, we're not quite sure what he was thinking about, but we'll guess that it's that you actually can use light in space. There's been a couple experiments done that show that light pressure can be very efficient in propulsion, sunlight in particular. This was a effort actually privately funded by the Planetary Society and demonstrated. Also, the Japanese Space Agency had a Icarus, a probe that demonstrated this. The problem is that sunlight doesn't produce enough power to get you to these, tens of percent of light speed, although it may get you to hundreds of kilometers a second, which is an order of magnitude better than we can do today. So we looked, and really our solution was to use sort of light sailing. We need to have the lowest possible mass for the spacecraft. We need to leave the engine and fuel on Earth if we can. We need to attach a sail to what we call a star chip, and I'll talk a little bit more about that, and use a humongous, that's a real technical term, laser on the ground. Well, you can calculate how big a laser do you need, and it's about a square kilometer. The amount of power is a few tens of gigawatts for a few minutes. This is probably doable today if you had a few $1 trillion. But just keep that thought. But there's a couple things that could change this. One, of course, I'll talk a little bit more about is the ability to make things really small. The other one is the rapid advance in laser technology and photonics, largely driven by communications technologies. That there is really tens of billions going in every year. Now, when we looked at this and we said, what's the cost of power for lasers? And it's on kind of a Moore's law type decrease over the last few years, and it continues to be on that curve. And the power you can get out of lasers is increasing. And when we looked at this and said, if this continues for 10 years or so, we'll be at the level where you could actually build a really huge laser that would have tens of gigawatts of power and would cost tens of billions, not trillions. And so that's one of the things that we're watching. The other thing is the size of spacecraft. This is a typical communication satellite today. It weighs, thousands of kilograms. But the question is, can you make that smaller? Just to point out that most of what a spacecraft does, the chip in it, if you have an Apple Watch, does that. So we came up with a concept that we could develop what we call a star chip, which is a spacecraft on a chip. When we have a prototype, and this is a picture of it, but I brought one with me. I challenge other people to bring their spacecraft in their pocket. This was produced by Mason Peck, a former chief technologist at NASA, who was a professor at Cornell. And these are real. A early version of this was flown with our support with the foundation last year. It was about the size of the envelope this was in, weighed a few grams, but demonstrated that it could be built and worked in space. So really neat effort, and we're continuing to do that. So the idea is, can you attach this chip to a light sail, probably not like this, and produce an interstellar spacecraft? Now, our schedule, based on this question, was that we're going to spend about $100 million over the next 5 to 7 years to determine the feasibility of some critical questions. And then we would like to build a prototype that we could launch in maybe 10 years, and then eventually the system in 30 years. The first effort of this is what we call the photon engine. We've made 11 awards, actually 12, that we're writing contracts right now on for the initial study phase, and then we'll narrow those down over the next few years to prototypes. We also have a technology problem with the sail. It has to take 50 gigawatts of power for a few minutes and not fall apart. So we're about to release some requests for proposal on that. And then there's a slight problem of communicating back from interstellar distances. This chip has a small laser on it. in principle, if you couple that to a small optical element, maybe even the sail itself, and then use the transmitter as a receiver, you can make this work. As I noted, we've started to look at a lot of the issues with all of these things, and I won't go into the details here, other than say we had some of the world's experts at this. The guy in charge of our laser efforts is Robert Fugate, who had something to do with laser weapons that the United States Air Force did or didn't produce. But again, I won't go into the details. But this is proceeding. We expect to publish all the results as we can. We want to do this openly. We would then build a prototype, as I noted, that would cost about $1 billion. I do note that Mark Zuckerberg is on our oversight board, and we haven't hit him up yet, but we will. And then there'd be a public-private partnership to launch to Alpha Centauri in the next maybe 30 years or so. Let me kind of close with our last major program, which is there any life elsewhere of any kind? Now, a lot of efforts are going on by space agencies, most of it focused on Mars. Although to me there's two really interesting places in the solar system that may be more likely to find any evidence of life. The first one is one of the inner moons of Saturn, Enceladus, which with the Cassini mission discovered that at one of the poles of this moon there are geysers of water being ejected into space. Cassini detected in these geysers some very simple organic or pre-organic molecules, carbon molecules. So this may be the best place to look. There's apparently an ocean under a surface of ice. So we are looking at the foundation of a potential privately funded mission to go and fly through these plumes and with some life detection, or at least life chemistry detection instruments. In fact, our big meeting with our sponsor is next week, so wish me luck on that. There's another place in the solar system that might have life. And there hasn't been as much discussion of this, but this is the planet Venus. Few probes we've sent there show that the top of the clouds in Venus has a pressure about what the pressure in this room is, and the temperature is about the temperature in this room. There are also evidence of some rather strange spectral features that could be produced by non-equilibrium gases. These are things that would be produced by life. So we're thinking about potentially also a probe there. Indeed, the European Space Agency had a probe a few years ago. The idea is that you might be able to drop something into the atmosphere and look. I do note that the technology to drop stuff cheaply back into the atmosphere, this was a NASA Ames project, small payload quick return, that has been tested already at least once from the space station. So this technology is there. But maybe the most interesting place is if we're going to go to Alpha Centauri, the nearest star system, is to see if we can find evidence of planets, and particularly life-bearing planets. The Alpha Centauri system consists of 3 stars. 2 of them are about the size of the Sun, Alpha Centauri A and B, and the third one is a small red dwarf star. Now, the really interesting is this: are there any planets there? And when we made our announcement we're going to go to Alpha Centauri, there was no evidence of any planets. But sometimes it's better to be lucky than good. So a few months after we made our announcement, the European Southern Observatory announced the detection of an Earth-sized planet in the habitable zone of Proxima Centauri. Really cool. They were nice enough to invite me there, and we were nice enough to give them a few $1 million to build an instrument. Of course, they already have a picture, so I guess we don't need to go there. But at any rate, the Alpha Centauri system is in the southern hemisphere. The instruments that we are using are the Very Large Telescope, and we should start observations next year with this instrument being built, and we can be able to, we hope, and this is in the infrared at 10 microns, directly image the planets if they exist around Alpha Centauri A and B. And as probably a lot of you know, the next generation telescope, which I guess Sweden is part of, is the extremely large telescope. which is actually big enough to not only directly image the planets in the Alpha Centauri system, but get information on their atmosphere, as well as the planet in Proxima Centauri. So we're in discussions about supporting some of those. And I'm always amused when I see these names, the Very Large Telescope and the Extremely Large Telescope. It's even more amusing to know that originally that was supposed to be the Overwhelmingly Large Telescope, but there was a budget cut. So the Overwhelmingly Large Telescope, that's what we're going to build when we send the probes to the stars. We also have a spacecraft that we're working. The Alpha Centauri system is kind of unique, as there are two stars like the Sun that orbit each other in around 70 years. They're a few arc seconds apart. It turns out we can actually reference one to the other and build a small spacecraft that would precisely observe over several years the orbits of one around the other. If there's a planet, we would see a small wobble. We can get about a millionth of an arc second. We could see a planet that's smaller than Mars if it's orbiting. This also would give us mass estimates, which we sort of need before we go there. So again, we're doing a number of efforts on that. The last part of our effort is we have an annual conference in April at Breakthrough Discuss Conference. A pretty neat conference. It's an invitation only, but if there are people here at the university, let us know. This year we're going to hold it the 12th and 13th of April. That, by the way, is the anniversary of Yuri Gagarin's flight. So there's a big ceremony that started in the U.S. about 12 years ago called Yuri's Night. For the last few years, Yuri's Night's been held at Yuri's, and it's a pretty neat party. But we're going to look at the question of the various possibilities for life. What would be exotic life? There's a lot of questions. What would machine life look like? We're going to talk about advances in propulsion. And then one of the key questions Yuri wants to do is have a public discussion of what would an alien look like from what we know, other than what science fiction thinks it looks like. Last year we invited the heads of science from most of the world space agencies. They mostly showed up. So we are working closely with space agencies around the world. These missions I talked about, these privately funded missions, we've already discussed with NASA and ESA. So if all goes well, sometime here, 2067, I probably won't live that long, but I might. Medical advances are good enough if I stay away from too much good food and booze. But a lot of you will live that long enough, so I think we've begun now. Well, let me stop there, and I'd be happy to answer any questions that you have, and hope a lot of you will join us in this really cool effort. Thanks.
Thank you for a very stimulating lecture. So I'm sure there are lots of questions. Let's see, there has to be something. Yeah, over there.
Yes.
Down here.
Would you include Titan among the bodies in the solar system that could potentially have life?
Absolutely.
More than Venus even,
Well, Titan is very interesting, and it has, a liquid, which is one of the things. It's, the hydrocarbons. There have been people that have discussed the kind of chemistry that you could produce. There is some evidence for non-equilibrium gases that would require some, or that a life-like process. So I think it's very definitely. In fact, one of NASA's New Frontiers mission possibilities is to go to Titan to look for life. In fact, we've actually discussed with NASA that, say, if they go to Titan, can we ride along and go look at Enceladus in detail? And they thought that was a good idea. As long as billionaires are willing to write checks to help them, they're happy to. But Titan is a very interesting location. I mean, it's it has a lot of the key characteristics. Venus is interesting again because you may have life on Venus, but it may be similar to Earth. The terrestrial planets over particularly the first few billion years, exchanged a lot of mass through asteroid impacts. So it's quite likely that at least even if it didn't arise on Venus, that life could have been deposited, at least in the upper atmosphere. Interestingly enough, we don't even know if there's life that exists in the Earth's upper atmosphere. It's a very hard measurement to make because of contamination. So that's one of our key questions, is how to avoid contamination on the spacecraft. But right now there's most of the world space agencies aren't really looking at Venus to look for life. So we think it's something we could do, again, to test out the technologies before we would go to the outer solar system. But Titan is very, very interesting. But we don't want to compete with space agencies. We want to work with them. Yeah.
When your starships or chips get to Alpha Centauri, what are their capabilities? What can they measure?
Well, the primary instrument we're looking at, and of course we can't stop with any technology. We know we just fly through. It's like a Pluto flyby. But the primary instruments would be cameras. We might be able to get some spectroscopy if we can get a spectrograph on that chip reasonably enough. We've looked at potentially if we fly close enough to the planet, and that's an argument how close you want to fly, is because the closer you get, the faster you have to turn to lock onto the planet. Maybe a magnetometer. We will probably send hundreds, if not thousands, of these. We're going to lose a lot of them in interstellar space through impacts with dust and so forth, and just failure over the decades they're in travel. But I think the primary instrument would be optical and infrared imagery. That you would, the sort of home run is that you fly by and there's oceans and continents and ruins of old civilizations or something. So Alpha Centauri is a little older than the Sun. I think it's about 1 billion years older. So it's maybe that'll answer why we don't see intelligent signals. Is they're all gone. Yeah.
Wait.
Okay, so you said optical infrared telescopes, but they are rather large, at least with the spacecrafts we have now. They usually are some 10-15 kilos.
Yeah, that's if you look at the camera in your iPhone, it's now getting to the size that you can do a lot. That you get pretty high resolution and record the data. The key thing is the optical element. So you need some sort of optical system that's tens of centimeters or so. But we need that same optical element to, after you fly by, you need to redirect it at the Earth and fire onboard that chip as a small, fraction of a watt pulse laser. So we need to figure out how maybe we'll use the sail is the optical element, or we might deploy, you might throw the sail away and deploy a small optical element. But it appears to us the technology to build a sort of Graham-class spacecraft that could get that kind of resolution, where you could get, tens of kilometers resolution on the planet is doable. But that's one of the research areas. But we felt it wasn't the most urgent one because that seems to be coming along quite well. Probably the world's expert in this is a young professor at Stanford who just started at Stanford, Zach Manchester, and he in the next year or so is going to look at beginning to sort of launch these sort of Graham-class spacecraft that have optical things that you can deploy a small optical element. So I think the technology is going to radically change our ability to do things. When I first got in the space business, space telescopes that could image the Earth and get meter-class resolution were thousands of kilograms, and they were billions of dollars. Of course, now there's companies that can produce just about that resolution with these CubeSats that weigh, as you said, 5-10 kilograms. And indeed, a couple of those guys used to work for me and have started some companies like Planet that produce hundreds of these. So, we need to go another 3 orders of magnitude, but I think that in principle that we're already on that path.
Actually, I have a question, and not a bit unrelated, but still, what do you think about manned space flight, like in the near future to Mars and so on? What do you think about that?
Well, I mean, that's it gets back to some of that existential question: is what is our future? And I mean, I've always believed that the future lies in humans expanding beyond the Earth. Of course, there's a lot of question what you mean by humans. Is it, do you download yourself in the machine and say you're still a human? But I think the next step is going to be to establish permanent human settlements, probably on the moon before Mars. I know in the United States there's a number of private groups that are working with the government or sometimes against the government. But people like Elon Musk and Jeff Bezos, they're high net worth people that have this vision of a solar system-wide society. Of course, I think eventually, I kind of agree with Stephen Hawking, who's talked about, well, eventually we need to go interstellar. Of course, we need to find if there's some place to go useful first. But I see the human part of it is really, one needs to separate what you do scientifically. And I think it's important that space agencies don't try to mix those things. I mean, having worked for NASA, a lot of the problem was that the science efforts in NASA are incredibly important, and they're generally not related to human settlement. But then there's a human spaceflight part that is related to that, and it's sometimes you'd get leaders of NASA that wanted to raid the other side of it. So usually this manned spaceflight wanted to raid the science side, but I think it's important to understand there's space science and then there's human space exploration. And they're different and they have different motivations, but they both need to go forward, in my opinion.
When will it happen?
I think there'll be a human settlement, permanent human, initially presence, but settlement by the end of the 2020s on the moon, and probably in the mid-2030s on Mars would be my estimate. A lot of it driven by, again, these high net worth people that, Bezos is now the world's richest person, and he told me a few years ago, he said he sells books so he could build rockets, and he seems to be doing pretty well in that. So I mean, he's got about 10 times the money that Elon Musk does. So and private, having been associated with private efforts, you can do a lot more with a lot less people. I worked for NASA with it was a really cool job. The second coolest I've ever had, where this is the coolest. But we had 2,500 people, and mostly just got in each other's way. For our foundation, the initiatives, the staff is 4, and we complain sometimes to our sponsor, but it means you can do things very quickly. We haven't sent too many memos to each other. You should just call on the phone and say, "What are you thinking?" But by the way, half the staff is here. Jamie Drew is our chief of staff, who's Swedish by background, so he says he speaks Swedish, but it's from southern Sweden, so it's not really Swedish. Is that right?
I could understand it. So it was okay, actually. Any more questions? Take the chance. Yeah. Yes, please. It's a microphone.
Sort of psychological question, really. I mean, we all here, we're kind of intellectuals and scientists, and maybe not all scientists, but we think it would be, I'm talking to SETI now, an amazing thing if we picked up a signal. We think that, but the general public, they've seen the movies, they've read the books. Is it going to be a big deal for them, or are they just going to say, well, of course, we expected it, so it's not a big deal?
Well, I think it's. I will say that it's probably the highest interest item with the public of any science question. I mean that when I used to fly on airlines, work for NASA, I'd wear my NASA jacket if I wanted to talk to the person. But the first question they'd ask is there life elsewhere? Is there intelligent life? So I think it's of positive interest. To be sure, some people are concerned about alerting some nasty aliens like Independence Day that would show up. Stephen Hawking's worried about that, for example. But I think that as long as you don't deliberately send signals, you're probably not going to get in trouble there. I'll also tell you that I've talked to world leaders in a lot of places, and every one of them is very interested in this. I mean, just 2 weeks ago, I met with the Vice President of the United States, and he was very taken with this project, thought it was really great, wanted to know what the U.S. government could do, and I've seen that around the world whenever you talk to political leaders. I think they find it as a fascinating question. Now, after we find it, it may be a different argument, but but it's like any science thing. The first thing you need to do is just, is there something there? And in fact, I have to say, just really pleased that in the last few years, the SETI question has re-entered the fundamental science question. I mean, I'm here because we have a conference today and tomorrow and Saturday, and I really want to commend the group here at the university that has set that up. That we're beginning to see a lot more focus again on, can we now with the technology we've got really make some advances on answering this question. That's. By the way, whoever discovers these signals will probably the most famous scientist in the world for a long time. Win both the Breakthrough and the Nobel Prize.
Bengt.
I'm curious about how you look at the division of labor between you and state agencies. I mean, do you think that you are in competition, or do you want to be complementary? And do you think there might be a risk that your activity becomes a reason for state agencies not to get involved in fundamental research so much?
Well, I think it's a very interesting question about basically we represent a really very old tradition in astronomy, which is, and I think particularly in the United States, was scientific philanthropy, where a wealthy individual feels it's important to fund efforts, and it's still the case that the majority of U.S. large telescopes are privately funded, and a lot of the new ones are being partially privately funded, not totally. There's always, of course, the worry that says, well, if you're going to do this, then the government doesn't need to do it. But it's important to pick something the government wouldn't do. And the things we're doing are high risk. Let me give you an example about the SETI question. We had our announcement meeting in London, and before the meeting, Yuri Milner assembled our kind of group that we had there, which included Martin Rees, the Astronomer Royal and former head of the Royal Society, and Frank Drake and a number of other scientists. And he asked us what we thought the probability in the next 10 years of finding an intelligent signal was. And sort of the answers varied between 0.1%, a few percent. And we asked Milner what he thought. He says, 10 to the minus fifth. And, I thought if I had gone to the U.S. government and said that I wanted to spend $100 million on something for 10 years, and my chance of success at my estimate was a few percent, and, that we wouldn't have gotten anywhere. And so I think it's important to pick those kind of projects that governments wouldn't do. At the same time, when we look at our efforts, the early phases are privately funded, and then later phases begin to be partnerships, and eventually maybe mostly government. So as I mentioned with Starshot, the initial research, which we're spending $100 million on, is something the government wouldn't do. The prototype, they may contribute to that, but it's still mostly private. But the full-scale system is definitely going to be government efforts, whether it's NASA, ESA, Chinese Space Agency, and so on. It'll probably be a global effort because it's probably tens of billions of dollars. It's like the International Space Station. So I think there's and we've seen, I've been a lot more welcomed in the halls of Washington, D.C. and otherwise than when I was a government employee. Usually when I was a government employee, when I went to Washington, it was to be yelled at for something. And then when I went to talk to somebody like the European Space Agency, they thought I was up to something. Okay, what American agenda do you have? But now everybody's very happy to work with us. And it's the nice thing about private foundations is that we can do things globally. It took us a few weeks to coordinate a joint effort with the Chinese government. I doubt if NASA could do that in a few decades, but then, so there's different things, and it's just recognizing those.
Okay, maybe a couple of final questions, please.
Like yours. And this as a second question, do you think that we are not educating people properly or spreading the right knowledge to these people so they
I mean, the basic question there is that, you know, we live in a society that is mostly not based on science, at least, and that and there's a distressingly large number of individuals, some of them are pretty high positions in various governments, that I wouldn't call scientifically oriented. I'm careful because I have to be nice to everybody. But the interesting thing to me, though, is a lot of them, when you talk to them, are actually more, you know, open. I mean, you know, flat Earth is, I mean, there's a tiny fraction of people that, I mean, there are bigger fractions of people that just don't accept fundamental science. But, you know, it was kind of interesting. One of my own personal experience, on my dissertation committee was a Jesuit priest who later became the director of the Vatican Observatory, George Coyne. And we used to call him Father Photon when I was in graduate school. Really neat guy. And if you'd ask him about, you know, science and religion, which is sort of what a lot of people are getting at, he rationalized them, you know, in a very elegant manner. I mean, he said there was a spiritual dimension to things, and then there was a physics dimension, and so he didn't see any problem with those. And I tend to find that if they're intelligent people, you can sit down and chat with them and come up to some conclusion. So I think it is certainly an issue that we ought to be aware of, that you know, questions like climate change and other things, that you know, it needs to be based on evidence, and it usually, I find it gives you an opportunity to discuss the scientific method and how it works. And I usually welcome when somebody tells me, well, you know, isn't the Earth flat? Or, you know, it's an opening to kind of, well, let's look at the evidence. But it's a challenge. It's a challenge to that we need to work all the time.
Maybe you had a question? No? No? Yes?
I have a question about the number of space chips you can build and the number you need to shoot at one system, and how many systems are you going to look at? Just Proxima Centauri or the 100 nearest stars?
Well, that's an interesting question. We hope in the next 10 or 20 years that we'll discover how many interesting places there are. So I think within 10 or 15 years, especially when the ELTs are finished and some space instruments, that we'll begin to have evidence of, okay, I don't know, there's 30, 40 stars within 10, 15 light years. We'll be able to survey the systems and find out, you know, how many, you know, Earth-sized planets are, or how many interesting planets are there, and hopefully begin to get some atmospheric data that says, okay, these are life-bearing and these aren't. In the end, I suspect we'll have a handful that look really interesting. You know, obviously the nearest one would be the best, and if we find that the Proxima b is got an atmosphere and seems to have some interesting non-equilibrium processes, that becomes a critical thing. If we find planets around Alpha Centauri A and B, and I'm guessing we will, you know, and I mean, if they're bare rocks, that's less interesting. That we would probably send over the course of a decade, you know, hundreds to the handful of interesting places. That's sort of the current thought to each one. The way we envision it today, we'd send about one a day. So, you know, you'd end up having a few thousand over, you know, a good bit of a decade. So it's, you know, obviously it depends on where they are. I mean, if we're going to go to Alpha Centauri, we got to put the system in the southern hemisphere, probably in the Atacama Desert. We mentioned that in some of our early talks, and we were contacted by the Chilean government, said, would you like to come and chat with us? And which we did. And they, I mean, actually I met with the guy that's the current president a few months ago, President Piñera, and he was quite positive, you know, how can we help? So was his predecessor. I met with Michelle Bachelet. So it's, you know, we just probably have to have another system in the northern hemisphere. You know, whether that's in the U.S. or China is obviously a TBD. By the way, the U.S. government's made it clear that they hope we're not working with China yet on big lasers, and we said no, we're working with them on other things. But that again, that's kind of the number.
Final question. Up there.
As I understood, you said you will send several thousands of these spaceships to Alpha Centauri.
Or, well, hundreds to whatever the interesting targets are.
What's actually the chances of getting there if many will be lost on the way?
Well, I hope it's reasonable. You know, it's the biggest concern we have is interstellar dust, and there's a pretty big what the density of interstellar dust is. If it's at the high end of the estimates, then we have a problem. If it's at the low end, we don't. You might be able to shield against really small impacts or have multiple, you know, components, but if you hit a piece of dust, it's a pretty bad event. The interstellar gas doesn't appear to be a problem. In fact, we think we can extract electrical energy from the, you know, the gas heating one side of the sail relative to the other. But you know, I mean, we'll probably do initial experiments where we're going at slower speeds in near interstellar space, you know, visiting the Oort cloud and so forth. We'll get a lot more data then. But right now, I'd say if we get 50% of them that get through, that's a huge success. If we get 10%, that's probably the minimum requirement.
Okay, I have one more duty to perform. We have a small gift here. It's from Costa Boda. It's glassworks in southern Sweden, founded in 1700s. And it's from a region called the Kingdom of Crystal.
Great. Well, thank you.
There you go.
Thank you much. Thank all of you.
Thank you very much.
Thanks.